So for our next speaker, we have Adam Wierman. Adam is a professor of computing and mathematical sciences at Caltech. Also, again, I guess the theme of the session, he has a variety of research. There's a lot of interesting work in energy and power and sustainability. If you were there for the panel earlier, you heard about some possible interesting future directions there. Also on networks, computing, safety, I think we'll hear about right now. He also has a Heavy Tails book I bet a lot of us are familiar with. Previously, he was an executive officer, which I understand to be a department chair, and he directs the Information Science and Technology Initiative there at Caltech. And he also has many awards for his research. I think a kind of enjoyable one to me is that ACM Sigmetrics has both given him personally a Rising Star Award and given one of his papers a Test of Time Award. So we've got some positive signal data on both state information and derivative information. So, Adam, it's great to have you here.
I like that way of explaining that. Thanks for the introduction. It's a pleasure to be here. It's great to see some folks who were at the panel earlier back again. Today, it's not in the title, but basically I view this talk as a pitch for stochastic folks and queuing scheduling folks in general to think about learning augmented algorithms. And so I'll try to motivate why, in our group, we've gotten very excited about these and have spent the last few years working on the designs of them in a couple of different application areas. There won't be a, scheduling question in this talk, but I hope that from seeing what can be done in sort of this domain and the type of best of both worlds, adversarial and stochastic type guarantees that you get from these learning augmented designs that can motivate you to think about how you might approach your problem with a learning augmented algorithm and what sort of guarantees you might get there. So that's the pitch for what I'm trying to do. And this is kind of an overview of a bunch of different papers with a bunch of different people. So the first line here are students working with me or co-advised with me at Caltech that have been working on the problems that you'll hear about. And then the bottom line are the external collaborators, although I guess Gwanan started at Caltech as a postdoc and now is faculty at CMU. So I'll give credit along the way for lots of the contributions to them. Okay, so jumping in, the motivation here for our group tends to come from the sort of common theme, common statement, nothing surprising here, that there's a ton of excitement around applying AI ML tools, in particular in the context of network systems like energy systems, power, data centers, communication systems, et cetera. And many of these systems, often the ones that we think about, are safety critical in the sense that you can't afford to fail at scale because things break, things go very wrong when they go wrong. And, you could cause power outages, you could cause outages of cloud services, these sorts of things. And these are just, unacceptable and have, very negative consequences in terms of cost and other things. And so, the big question is, are ML tools ready for these sort of safety critical applications? And I think, the answer is a resounding no at this point. There's many failures one can point to. These are all a year or two old, but every moment you see, even the places where you see it working very well, and you think of these Boston Dynamics types demonstrations, there's just as many failures and in these well-scripted things, and you see these failures all over the place. A place where we spend a lot of time thinking in our group at Caltech is around the design of sustainable data centers. And this is a huge success story in general. Over the last decade, we have moved to a world where now renewables are integrated very tightly into cloud scheduling and cloud resource allocation of servers. And these servers are often allocated in a way where you run more work when it's windy or it's sunny, when renewables are available in the grid, and you sort of defer work in situations where there's brown energy available to you. And this is a huge success story, but it's one where you think without knowing the details that this is probably a success of, AI-driven control, and there are even headlines to that end, right? So DeepMind had a very splashy set of research projects around, showing that you could reduce cooling bills, you could improve sustainability with these DeepRL type tools. But when you look at what these companies are actually deploying in their industry side, there's no AI to be found. What they're actually deploying is online robust optimization techniques without the sort of ML AI insights coming from places like DeepMind, even within Google, where you might think there would be a bias towards using these tools. And the reason is simply you can't afford to fail at scale. You can't afford for something to go wrong in an unexplained way with your AI tool, whether it be because of training failures or distribution shift or any number of things that are hidden in the deep model that you've trained and are trying to deploy. The lack of interpretability, the lack of explainability really leads these things to not be useful yet in safety critical systems. And to give you an example of what the fear is that leads to this is an example I'll come back to later in the talk. This is kind of a small scale numerical simulation of sort of capacity provisioning in a data center, determining the number of active servers in each state and the location of workloads in a system where you have on-site solar and on-site electricity storage to try to help manage it. So a typical sort of small scale sustainable data center design. And what I'm showing on the axis here is the cost, which includes sort of a carbon cost, as well as a penalty for missing workloads and just the operation cost of the cloud. And the y-axis here is the interesting one. This is distribution shift between training and testing. So this is pretty simplistic. Think of the mean shifting, and we can control it because we're doing it in simulation. And the black line is our sort of standard online optimization based approaches that you would pick up in the literature. And the blue line is a DeepRL based approach. And so you can see there's, we're not seeing the 40% here that DeepMind found in their experiments, but you see a very significant increase in or reduction in cost improvement in the situation where your training and your test match, where there's no distribution shift. So this is a big win if things are going well. But you see a huge risk in the case that there's distribution shift, in the case that you're off in your training, and when you deploy, something has happened. There's a burst of load for whatever reason, or a strange weather pattern comes through that you haven't trained well for. And this can lead to way bigger damage than the gain you're getting from the good situation here if you're off in these ways. And I didn't put units, but these are not major in terms of this is on the order of 5-10% style shifts in these workloads. And so you can really pay a lot with small deviations in this situation. And this means that you can't adopt these ML type tools. What you'd want is something that looks more like this green line, where you have you're capturing most of the gain in the case that your training and everything matches, but you're still maintaining, close to the robustness level of these non-ML based solutions in the event that there's some sort of distribution shift. So this is, if you could give a curve like this, then you could actually take these tools and deploy them in these safety critical systems. But something like the blue curve is not ready for the show yet. And so, the goal of kind of the research agenda is sort of summarized in this figure. Can you find a way of layering something on top of these learning tools, or vice versa, layering something on top of the online optimization tools so that you get a best of both worlds, so that you get some sort of strong robustness guarantee while also capturing the gain from ML if it is trained on the right data and performing well. And so, in a sentence, that is, can the guarantees required by safety critical applications be enforced by AI tools? And, in a sort of caricature, Pareto optimality graph. The current world looks like this. You have all these black box AI ML tools that do very well for performance where they're well trained, but are not as good for robustness and safety, have really fragile behavior there. And then you have these sort of more classical control online algorithms that are good for performance, but not as good as the AI ML tools, but give you very strong safety and robustness guarantees because of the work of this community, for example, in providing those things. And so what you're trying to do, with learning augmented algorithms is expand that frontier and combine them in some way. And so some people term this, combining model-free and model-based, and in that language, there's a ton of work in the, learning plus control community that has emerged in the last 3 or 4 years that take various ways of adding structure to model-free approaches in order to get some stronger guarantees, or take various ways of adding learning dynamics to model-based approaches to optimize within some policy class, to sort of doing adversarial testing of the model-free approaches, or verification somehow, system verification type techniques of the model-free approaches. There's a huge, variety of approaches people are taking to try to get that middle ground. And what I'm going to talk about today is one specific approach for doing that, which is a very, I'd say, simple and black box way of trying to get to that middle ground. And as a result, something that I think can be applied very practically and can be studied in a wide variety of applications without needing specific structure in the application to apply it. And so this is, what I'm calling or what the community calls learning augmented algorithms. And the particular approach that, I'm going to be conveying is often referred to as untrusted advice or untrusted experts, as the sort of tagline here. And, at a high level, what it does is it says, however you are training your AI tool for your problem, whatever it spits out, that's untrusted advice. And we have that untrusted advice giving us some suggestion of what to do, or some estimate of cost functions, or some prediction of some other thing that you're going to use to make a decision. And then on the other hand, you have a trusted expert, your classical robust optimization or control policy, that is spitting out trusted advice. And what makes it trusted advice is that if you follow this, you're going to have a particular guarantee on your performance. So there's a trust, that goes along with it, of a performance bound or, provable bound that goes with it. And then the task is to take that untrusted advice and combine it with your trusted advice in a way that you maintain merely the trusted guarantee while exploiting the untrusted advice in the situations where it works well. So that's the high level goal. And sort of in a system architecture type diagram, this is what you can think in your head. So at any given point when you're making a decision, whatever system state or input you have comes in, you funnel it both to your black box AI tool and to your online algorithm. They spit out what they would do. You can think about it simply right now. They spit out maybe a potential action that you could follow. And so one is the action that will give you a guarantee on, say, your performance bound or your safety bound. And then the other is something that most of the time will work really well, but you have no guarantee about it. And then your goal is to design a meta algorithm that takes these as input, spits out an action, and hopefully maintains best of both worlds. And so then the research question, the most dominant one, is how do you take these two advice and switch between them or combine them in a smart way that keeps the guarantees you want? And what do I mean by the guarantees that you want formally? These are the two ways that the community has formalized it so far. So they formalize it and give them the terms robustness and consistency, where consistency is capturing you do as well as the untrusted advice when the untrusted advice does well. And the way we capture that is still adversarially, but you'll see that the adversarial is sort of not the key thing here. So you're saying that your cost is within a 1 plus delta factor of what the untrusted advice achieves. But of course, if the untrusted advice is terrible, this is a trivial thing to satisfy. If the untrusted advice is near optimal, now this constraint bites. And so basically this is saying if the untrusted advice is near optimal, you need to be near optimal. And so that's consistency. Robustness is the more classic one that says adversarially, you satisfy some approximation ratio or competitive ratio, gamma alg, and sort of vaguely a little bit right now, your competitive ratio gamma should be close to the competitive ratio of the trusted advice. And clearly there's going to be a trade-off here. So this gamma alg will depend on the delta. If you're really close to following the untrusted advice, you're going to give up something in terms of your robustness property. And so sort of the game here is what is the optimal trade-off that you can achieve via consistency and robustness? Can you lower bound that trade-off? Can you identify what it is precisely? And then can you design algorithms that hit that trade-off between consistency and robustness? And so that's the sort of core algorithmic question in this domain. And there's a bunch more variations of this that I'll come to after we spend some time to give you a flavor for the broader research field in this space. But this is the core, is, you know, what sort of trade-off can you achieve between consistency and robustness in a meta algorithm that is combining untrusted advice with trusted advice. And now, you know, we just heard about, you know, experts and bandits being applied in these sorts of contexts. This is, again, very reminiscent of experts and bandits, and there's a lot of connections you can make. The extra work you have to do here is that, you know, one of your arms has a guarantee. And so all of your analysis, all of your derivations, all of your algorithms are sort of modulated by the fact that, you know, if you follow one arm, you're going to have a provable guarantee, and you don't want to give up too much compared to that provable guarantee. And so how do you explore, how do you mix in the other arm to take advantage of it, but not give up that guarantee? And so there's a slightly different style of how you mix in the results you get as a result of that trusted guarantee that you're trying to maintain. And just to make it really concrete, if we, you know, think of, you know, classical control, model predictive control, MPC, is the idea of like certainty equivalent predictions. So you take whatever predictions you're given, you compute the optimal action given those predictions, and then you follow the first step of that optimal trajectory right now, and you just do that in a receding way over time. As you can imagine, this is great for consistency. If your predictions are perfect, you're going to be near perfect if you follow MPC. But if your predictions are bad, you're putting, you know, certainty equivalents, you're treating them as if they were true. And so you suffer dramatically. And you can see this, just to make it concrete, in an example I'll come back to later. So this is a drone trajectory tracking simulation. So imagine, you know, this is a simulator of a drone that's trying to fly and follow this path. It's not given the path all ahead of time. It's given predictions of what the path will look like at each time. And those predictions can either be perfect on the left or way off on the right. And you can see, if you use MPC in this world, if the predictions are great, you're doing great. If the predictions are terrible, you're in trouble. And, you know, this is really, I think, making concrete the idea that you want consistency to be able to take advantage of the ML/AI tools, but without robustness, you can be led astray very easily. And so you need to do something in this meta algorithm to protect robustness given the predictions. Okay, let me pause here and just make sure, since these concepts are so important, are there any questions about these concepts? I'll make things more concrete once we get into like a specific application. We talk about specific results, but already I hope the intuition between these concepts are clear. Okay, good. So one thing I'll say, actually, I wanted to add for this community is consistency in this definition is a sort of adversarial notion. In some contexts, what people mean by consistency is actually an average case notion. So a more stochastic notion, where consistency is you've designed your policy in a stochastic world and you want it to perform well in that stochastic world, given the predictions, and so you have a sort of average case, more classical kind of queuing or scheduling result there, and you want that to be near optimal if your predictions are good, but then your robustness is worst case. And so then you're truly kind of bridging the worst case and the stochastic worlds with these definitions. And so there's some flexibility depending on the problem and the application, exactly how you formulate consistency. Okay, so this, as I've defined it, is a really, I'd say, exploding area. I'm participating in a Simons program this fall that has a large fraction of the activity around it, around questions like this. And it's sort of in this lingo and in this type of formulation emerged in about 2018. So we have 4 years almost now of work in this space. And there's just a huge set of models that are, are looked at in this space. And, many are in the sort of online algorithms world, like online set cover, online matching. Everything started in ski rental for this, but a number are in more stochastic contexts, like the LQR, linear quadratic control type work, and scheduling work that happened recently with Ziv Scully and Isaac Gross and Michael Mitzenmacher. And so it's starting to make its way into more stochastic contexts as well. And if you're curious of just sort of an overwhelming intro to this space, there's a very useful paper repository that has been formed that is, I think, up to like 130, 140 papers at this point, all within the last couple of years, looking at different models and improving on people's results. That it gives you an overview of what's going on in this space. So it's a very exciting area to be in right now. Okay, so that's my motivation. So hopefully you're intrigued. Now to make it more concrete, what I'm going to talk about today is sort of a couple of insights around how you design algorithms, these meta algorithms for this style of untrusted advice, learning augmented algorithms. And so my focus is going to be on trying to sort of give you fundamental limits on different styles of algorithms with these results, rather than focus on giving you a survey of the best algorithms and the best results in a bunch of different areas. I want to use just a couple areas to highlight fundamental limits on how you think about designing the algorithms. And so to that end, I'll look at 3 applications: convex body chasing, online convex optimization with switching costs, and a particular adaptive control problem at the end. Okay, and so that's our agenda. And for each one, we'll learn like a little bit more about these fundamental limits is the hope. Okay, so convex body chasing. So for this community, some of you might be familiar, but I probably not everybody. But it's a nice problem to do this intro with because it's very easy to draw a picture of and understand. And so it's a very classic problem in operations research and optimization. And so the idea here is think of this as a very high dimensional space. There's some initial point that you're in. At every round in this online problem, you're presented with a convex body. And you have to choose a point to move to within that convex body. So the constraint is you're moving to somewhere within that body. And there's no difference in cost. There's no cost here in terms of where you are in the body. The only thing that you pay is your movement cost for how far you move to get into the body. And so if you're greedy, you might just kind of project yourself onto the closest point of the body. But of course, if you do that, the adversary might give you a body that's very far away on the other side. And now you have to move again, whereas otherwise you might be able to might have been able to stay still. And so this happens over and over. Now you get a new body. If we had been smart and moved to this part of the body, we wouldn't have to move again, but we got unlucky. We moved here. And so now we have to move. We move in. Now again, if we had been smart and lucky, we might have moved here, but we didn't know what was coming. And so now we have to move again, and we move there, we pay our distance and so on. And so the total cost that you pay on an instance is the sum of your distances. And at every given point, you have to move within this convex body. So that's the problem. Very simple to explain. And it's very clear why this is hard, right? So it's hard because you don't know what's coming. And so without knowing what's coming, where do you move within the body? There's nothing to give you that information. So how do you hedge? And it's also very clear that predictive tools could be very useful here. If you could predict where the next couple of bodies would be, that would give you a lot of information about where you should move within the current body. And so if you have some sort of data-driven idea, predictions about what's going to happen in the future, you could really exploit them here if they were good. And so it's a good, problem domain to think about, these sorts of data-driven algorithms. Okay, so this convex body chasing has a long history, many applications, lots of applications these days. I'd say most of the applications are to safety, decisions with safety constraints. So think about, for example, control decisions where you need to be in some safety region at each point in time. And so you're trying to stabilize the system, but you always have to constrain yourself to be in a given safety region. And it's also a sort of deceptively simple looking problem. It turns out that you can reduce this to various large, broad problems in online convex optimization and online control. And so if you can give good algorithms for body chasing, you immediately get good algorithms for online convex optimization and online control problems as well, which leads me to those being the second and third applications in this talk that we'll talk about. It's been a problem that's gotten a lot of attention in the last 5 years, 6-7 years at this point. So many of the initial results were by sort of Nikhil Bansal's group and collaborators. And then in the last few years, Sebastian Buback and Mark Selk and their collaborators have really pushed the limits. And at this point, the state-of-the-art algorithms in terms of the classical worst case type bounds are this. So there are various versions of Steiner point-based algorithms, so functional Steiner point to be precise, where you basically move to a particular center, the Steiner point of each set. And it makes intuitive sense. You want to move to some notion of the center because if you're in the center, the adversary can exploit you the least in terms of where they put the next body. And so you have to be very conservative in the adversarial thing and move to some notion of the center of these bodies. And this is one way to do it. And this gets you a competitive ratio that's order D. If you tend to not want to have the time horizon there. D is the dimension of the problem. T is the length of the time. And so, it's nearly root D. There's a log T there that's quite annoying. The lower bound is root D, but if you want a time independent bound, the best known right now is order D. And so there's still a little bit of a gap, but not much given that log T is often not too bad. And so this is sort of the art. And as I said, like the sort of, this is a very strong, very beautiful theoretical result, but from a practical perspective, it sort of highlights that you have to be overly conservative in this adversarial model because you're always moving to the middle. And if we come back to our example, as I pointed out, if you had the right advice, you could just move once and never move again, and your cost is just way better than always moving to the center. And so if you can have a tool that can give you good advice, you should be able to exploit it. But of course, if the advice were bad, it could be, guessing that the next body would overlap here and be wrong, guess wrong again, and now it's a disaster. And so this really highlights why you want consistency. You want to be able to take advantage of the predictions when they're good, like this case, but you don't want to be hurt in situations where it's bad, in this case. Okay, so that's the intro. Are there questions about the model at this point? Okay, so moving on then to designing the algorithms. How do you think about algorithms here? Well, the most natural way to think about them is I'm either going to follow the untrusted advice or the trusted advice, and I want to kind of follow maybe the untrusted advice until it proves to me that it's bad, and then start to switch and follow the trusted advice because I've learned that the untrusted advice can't be trusted, and if the untrusted advice is trustworthy, then I just stick with it. But of course, it might be untrustworthy at the beginning, and then trustworthy, and then untrustworthy, and so this is all adversarial. So how do you do this in a way that you're really getting a guarantee becomes the trick, and So that's one question. And also because of that notion of needing to pay attention to how it's done in the past, to know whether you can trust the untrusted advice, it's pretty clear that some notion of memory is needed in these algorithms, or you might expect that some notion of memory is needed in these algorithms. And so then the question of how much memory is needed, how much information do you need to store about the past? How can you do that in a compact way becomes a very interesting one for these algorithms as well. And so those are the things that I'll focus on. And we'll start with switching. So this is, I'd say, anybody in this field, the first thing they'd write down is a switching algorithm that looks like this. And this would be their starting point for evaluating, the baseline for this domain. And so what do I mean by a switching algorithm? This is a switching algorithm using the doubling trick from online algorithms. And so basically, you have to, you start with following the untrusted advice. And why start with untrusted? Well, because if you want consistency and your first step is to use the trusted advice and the untrusted advice is perfect, the adversary just stops the instance and you look terrible. So if you want to have a 1 plus delta consistency bound, you have to start by following the untrusted advice. And so you start by following the untrusted advice. And then how long do you follow it? Well, let's follow it until some amount of time and distance r is traveled. And then let's switch to the trusted advice, and we'll follow that also until a distance r is traveled. And this has the magical, effect of saying, if the untrusted advice is bad, we'll spend less time steps using it because we'll incur our cost faster. And if it's good, we'll spend more time steps using it because it will take us longer to incur our cost. And so whichever one of these is doing better, we'll spend more time using it because these costs are both R. And so this biases already in terms of your exploration towards exploiting the one that is doing well. And you can't stick with one or the, after you switch, you have to be able to go back. And this is where the doubling trick comes into play. If each time you double R, then you make sure that the time you could be stuck with a bad algorithm is bounded in terms of the total cost you've already experienced. And so you can't be hurt too much because you're never going to spend more than 1/2 of your total cost incurred so far using a given algorithm in a given stage of this. And so that gives you a protection factor. And so this is the toy version of it. And, as you might imagine, why double, why choose these exactly the same? What you want to do actually is optimize R, and the choice for these R isn't actually the same for both of them. It's dependent on what the performance bound is you have for your trusted advice. And so you can optimize that to get the right performance bound based on the trusted advice. And you optimize it based on the trade-off you want to achieve between consistency and robustness. How close to optimal do you want to be for the consistency bound versus how much are you willing to give up for the robustness bound? And so all of those go into the choice of R. And then the other thing I want to emphasize is this is really simple, right? Because here, I don't care how you're doing, what deep RL model or what you're doing there. It doesn't matter. It doesn't impact this algorithm at all. It's just a black box. And I don't care what you're doing under the hood for your trusted algorithm either. All I care about in selecting the R is the guarantee you tell me you can enforce with your trusted algorithm. And so none of the details of those matter. They're just pure black boxes. This is a few lines of code on top of the advice they're giving you, and you're done. And so it's very simple, easy to deploy. And like I said, you optimize R to bias things. And the guarantee that you can get for this is work from that appeared in Cult this year from Nico and Tinashe, who are students at Caltech. And this is the first version of it I'll show you. This is for the nested case. So this is the case where the convex bodies in the next round are always contained in the convex bodies previously. And you'll see later in the talk, this is an important subcase for adaptive control. But for now, this is just an easier case to start with. And so for the nested case, this simple switching algorithm with optimized Rs gets you 1 plus delta consistent and D over delta robust. Now remember, D was the best competitive bound you could have if you ignored advice entirely. And so we're paying a 1 over delta factor to get a delta closeness to the optimal, or to the untrusted advice when it's near optimal. And so this is like delta versus 1 over delta. And so, this is a powerful result already, because this says, whatever complex deep RL model you're deploying, with no additional work, you have a provable adversarial bound on the robustness of that learning rule. And all you have to do is mix it with a trusted algorithm that exists in the literature already to get it. And so this gives you that really well. And so you get the benefit of your stochastic analysis and everything you've done to study your AI tool, but you immediately can wrap around a adversarial bound on top of it. Okay, so that's the starting point. Now, this was nested. So what happens when we go beyond nested? I started with nested for a reason. So now there's a fundamental limit. And so now we can start to talk about, things get a little interesting here. It would not be very interesting if the simple algorithm worked really well, always. And so here now, what we can prove is that for the general case, any switching algorithm, no matter how you switch, no matter what rule you use, has to give up at least a factor of 3 in consistency. And this is now disappointing, because now your deep RL tool can be optimal, and by wrapping robustness on top of it, you're giving up a factor of 3 of optimal, which is just unacceptable in most practical applications. All right, so you're giving up almost all of the gain, or more than all of the gain, from using the complex learning tool, because you're wrapping robustness on it in this simple way. And so this means that we want to go beyond switching algorithms. We want to look at something more complicated, more adaptive, that instead of just always choosing one or the other, takes advantage of convexity. And in this problem, the key thing to take advantage of is convexity, because you know that the convex combination of the 2 advice points is guaranteed to be still in the body, since they're both in the body. And so you have your untrusted advice in green, your trusted advice in blue. You know that everything on the line between them is in the body. And so the question is how to adaptively choose a point on that line. So this is a problem called like bicompetitive line chasing, because if we think about what we want to achieve, we want to be competitive with the cost of the trusted advice. And we want to be competitive with the cost of the untrusted advice. So we want to be competitive. We want to have an adversarial approximation ratio with both endpoints of the line at any given point. And so how do we adaptively choose a point on the line so that we achieve a bicompetitive bound with both endpoints of the line always? That's what the problem can now be boiled down to, which is very, again, a classical online algorithms, online optimization problem by competitive line choosing. And so how do we do that? Well, I'm not going to give the full nasty details of how you do the adaptive step size, but one case is easy, right? If you know that the trusted algorithm, the cost you've experienced of that over the whole history, cost t is the cost up to time t of the trusted algorithm, x, and this is the cost up to time t of the untrusted algorithm, x hat. So if you know that the cost of the trusted algorithm is better than the cost of the untrusted algorithm, then just follow. I don't know why I have much there. If it's better, just follow the trusted algorithm, because then you have the guarantee and you're doing better than the untrusted algorithm. Done. But in the other case where the untrusted algorithm looks like it's performing well, how much do you trust it? Now, you're taking a greedy step towards the trusted one, and the size of that greedy step depends in a fairly complex way on the ratio of those running costs of the 2 algorithms. And so that's the high level of how the algorithm works. And this sort of adaptive approach, again, is completely black box to how the trusted and untrusted algorithms work, but it now uses full memory, because it uses the whole memory of the cost experienced by the algorithms up to that point, which is something that we'll come back to. It's a lot of information, but doing that, we can get a result that is weaker than the nested case, but is still now much more positive. So we get a bound that is root 2 plus delta consistent. So that's root 2 is lower than 3. So this is, a 1 point whatever, consistent bound. So it's not giving up a ton. I think this is now reasonable in many cases, especially since this is adversarial. You would expect this to perform pretty well in most practical situations. But notice that we're now giving up a delta squared in robustness instead of a delta in robustness like in X. So you're paying more in robustness to maintain a close bound on what you're to exploit the learning tool. It's harder. It's, you have to give up something in robustness to exploit the learning tool. In the general case, you have to give up something more. And this is again in the Colt paper with Nico and Tinashe. So a really interesting open question in this problem is, our best result so far says that you have to give up something. This is not a 1. This root 2 is strictly larger than 1. So you have to give up something to achieve robustness in this context. Is that a fundamental limit or not? We don't have a lower bound showing that it is. I don't know. I used to say I think we have it nailed. Now I'm not so sure. Actually, I would not put money either way in terms of whether there's a better algorithm with a lower than root 2 or not. So I think that's a really interesting open question. And we're also not sure whether this delta squared is necessary or whether it can be pushed to delta instead of delta squared. Okay, so that's our first piece. And so that is an example of this first question. When should you switch? Well, you can't get away with just switching. You have to be willing to take advantage of some more structure of the problem if you want to get really good bounds in this context. And in the body chasing problem, we took advantage of the convexity of the problem to look at adaptive combinations of the two choices rather than being stuck with just following the two choices. So next I want to do memory. And so as we saw in our adaptive algorithm, you needed full memory of costs to get the bound we were achieving. Is that a fundamental limit as well? That's what we'll explore next. And we're going to do that in the context of a problem that is actually equivalent. So there's a reduction between body chasing and this one, but here there's extra structure which sort of lets you get a better feel of where hardness is coming from in the problem. And so I want to introduce this problem to sort of highlight that hardness a little bit better. And so here, this is online optimization with switching cost. It's very similar. So again, you have an action that you're taking in high dimensional space, and at each round you're presented with a cost function. You now move to a new action, and here you pay a cost in addition to movement. So you pay your movement cost, your switching cost, but now additionally you pay a hitting cost, which is the cost of your action on that cost function. And so, this feels a little bit more complicated. You can reduce the two to each other, but, it feels a little bit more complicated because of that cost function, but it's still a fairly simple problem to explain. And again, you get a new cost function, you move again, you pay the cost on that cost function and so on. And so now you have your movement cost that you had before, according to some norm, but you have this additional hitting cost term, which you can think of. I've drawn everything as convex, but the problem, is interesting both when these cost functions are convex and non-convex. And actually, I'll be talking about the non-convex case here, which makes it a little bit more interesting in general than the body chasing problem. Okay, and so same problem as before. Without knowing future costs, how do you decide where to move to? Boy, predictions would help. If you knew something about the future costs, you could be very smart in your movement. But if those predictions are bad, you could be fooled really easily. Okay, so again, it has a long history. This has been, a passion model of mine for, over a decade now. We've been doing variations and algorithms from this space, starting back in the, in the early 2010s with single dimension versions of this problem and applications of them to sustainable data centers. But these days, there have been kind of industry deployments of algorithms related to this problem in data centers, video streaming, EV charging, camera tracking of NBA games, online control of drones, portfolio optimization, et cetera. So it's a very widely applicable problem, and algorithms here can have a really almost immediate impact in a lot of these application settings. And so, there's been a long line of work for multiple decades, but just in the past few years, there's been some really exciting work that has nailed a couple of the interesting, most classical versions of this problem. And so just to summarize one line here, which is most relevant to this talk. So here, if we think of the cost functions as being alpha polyhedral, so living in some sort of cone of slope alpha, then the hard ones are the case when alpha is small, because then you're very shallow around the minimizer or around your local minima. And here, this is not implying convexity, so there can be not convex and non-convex problems that are alpha polyhedral. And in the convex case, there's a memoryless algorithm ROBD that can achieve root 1 over alpha competitive. And this is tight. Actually, it's kind of amazing. This is a place where it's tight up to constant factors in terms of what it can achieve compared to what any online algorithm can achieve. And then in the non-convex case, it turns out you're kind of limited. The best known algorithm is a greedy algorithm that just moves to the minimizer of the per round cost, because otherwise adversarially, the non-convex functions give the adversary a lot of power to really exploit anything you do that's not greedy. And so, it's not proven that this is the best possible, but you can get 1 plus alpha with a greedy algorithm, and no one's been able to do better so far in that space. And so those are sort of the state of the art currently. And again, I won't dwell on this much, but I think it's pretty easy to see that if you get good predictions, I'm not going to scroll through this, but if you get good predictions, things are really good. You can avoid lots of movement. If you get bad predictions, you can be fooled really easily in this model and take way extra moves, way longer moves than you need to, because you think it's really important to be near this minimizer. And then, the next minimizer is right where you just were, and you're in big trouble. And so, very a problem that's ripe for looking at these sorts of untrusted advice frameworks in. Okay, and so just like before, we'll start with a switching algorithm. In this case, I'll just jump right to it. It's of the flavor of the one previously, but now the rule for when you switch depends on that running cost. So you have to pay attention to the cost that you've experienced over all time up to current time t. Look at that ratio between trusted and untrusted, and that gives you your switching rule. But the details of that switching rule aren't the important thing. The important thing is there's a switching algorithm that's adaptive, that can achieve this particular guarantee. And I'll say a bunch of this. This is joint work with Don, who's a student at Nico again, Don, who's a student at Georgia Tech, and Deb McCord at Georgia Tech as well. And so here, I'll say a few things about this. So first, this is for the non-convex online optimization problem. And because things are non-convex, if you do something other than switching, you're in trouble, because there could be, something with two local extrema, and you try to take the combination of them in some adaptive way, and just happens that there's a big hump there, and you get punished for trying to be in the middle. And so you have to be doing switching algorithms here to get any sort of adversarial robustness guarantees. And so that rules out the style of algorithm that helped us so much in the body chasing problem. So that's one thing I want to emphasize. The other thing is I'll sort of emphasize again, this is a black box algorithm. So you get for your deep RL problem that your deep RL algorithm that you've designed and carefully tuned, you apply this here and you immediately get an adversarial robustness guarantee. Here we're getting the 1 plus delta. I have the 2 there just to make the right side look a little bit simpler. Consistent, which is great. So you're not giving up anything compared to the deep RL, except for the trade-off you're making to get robustness. But, here the trade-off with robustness is much more extreme than we saw in the body chasing problem. So you really can pay exponentially in terms of this consistency parameter in an adversarial sense with your robustness bound. And so this is a much more challenging domain. It's harder to have robustness guarantees and exploit untrusted advice here, which I think is quite interesting. And this is not a function of our weakness of analysis. The constants here could be improved, but there's a exponential trade-off provably necessary here for any online algorithm in terms of the trade-off between consistency and robustness in this non-convex setting. I'll come back. The convex setting gives you more structure and you might be able to do better. And some results like that are quite interesting. Some follow directly from the body chasing work, but others, taking advantage of particular structure are quite intriguing to still go after. Okay, but now the point of coming to this model was to look at memory. So this uses full memory again in our switching algorithm. And here we can prove a fundamental limit. And so the fundamental limit here is that if you're in 2 dimensions, even if the domain is just convex, not exploiting non-convexity to make this harder, and you have alpha polyhedral costs, then any memoryless meta-algorithm cannot be both finite robust and have a consistency bound better than root alpha. And if you remember, root alpha was achievable by this ROBD algorithm in the convex case, which doesn't use predictions at all. And so if you want to benefit, basically this says that if you want to have finite robustness, you can't benefit from using predictions in terms of what you could do with just ignoring them entirely in an adversary model here. And so this is, there's a few interesting things about this result. So first of all, this is not saying you need full memory. This is saying if you have no memory, you're completely memoryless. You can't benefit from predictions. And so how much memory do you need is still a nice open problem. And the other thing that's quite interesting here is that this, definitely relies on being in 2 dimensions. And there's really interesting problems in 1 dimension, actually. So the 1-dimensional case is, has been applied in the data center world, for example, and has a large literature just in its own. It's a challenging problem in its own right. And in the 1-dimensional case, you can be memoryless. And so this took quite a bit of work, actually, to get this result. In the 1-dimensional case, you can have a variation of this regularized online balanced descent algorithm, ROBD, that is adaptive, that gets a 1 plus delta, 1 over delta squared trade-off between consistency and robustness. And this is, again, work with Deb and Don and Nico. And here again, there's some nice open questions. We don't know that this 1 over delta squared is optimal. This is one case where you can get away with memorylessness. Where else can you get away with memoryless algorithms in this adaptive world? I think is a really interesting question. And I'm realizing I'm going much slower than I thought. So let me show you an example. I have a third module that I was hoping to do, but I guess I'm going to have to do that very, very quickly. I just wanted to come back to my motivating example. So this is my motivating example of data centers from the intro, and that green dotted line that I put up there as a goal, that's basically achieved by the algorithm I just showed you. So this adaptive online switching algorithm, you deploy it in this data center problem, and this takes that DeepRL model and achieves nearly it in this case, and gets a very good performance even under significant distribution shift. And so this plot is very useful in showing that exponential trade-off between robustness and consistency is adversarial, and that in many situations you don't pay anywhere near that exponential trade-off in terms of the robustness versus consistency bound. And so you can really, these algorithms work. And this is a few lines of code on top of models that already exist. And, all of a sudden you're getting a best of both worlds. So I think it's really interesting. And we're working now with a few industry partners on deploying things like this in sustainability problems and management. And similarly in the drone tracking problem, these are the 2 figures I showed you before. If we take even noisier predictions for MPC, it gets destroyed. We run the algorithm I just showed you about, and the blue line is, you see a few deviations of it from the trajectory that's supposed to track, but it looks nearly as good as the perfect predictions MPC, despite being fed terrible predictions. It's very robust to those in this model. Okay, so I'm going to go quickly through. I'm going to have to just skip my third module here. So let me not rush, and let me just highlight that my goal was to show you fundamental limits for these data augmented algorithms. And I think the insight here is that switching can work successfully, but you can often do better if you can exploit structure of your problem. Memory seems to be really crucial, but it's not clear yet how much memory you need, how to use memory, when you can get away without memory in these algorithms. And these are all really interesting questions. And I think, it's a wide open field, and especially in, classical queuing scheduling domains, you can ask all the questions I just asked, and they're completely open and really interesting and impactful. And then if I come back to my kind of architectural overview, we focused on one question in the field. There's many, many others that are really interesting to study. And so, I introduced you to robustness and consistency as the most classical notions. Classical is weird for a 3-year-old field, but it's the most common notions of metrics here. But smoothness is really important. I mean, right now, robustness is one extreme. The predictions are terrible. Consistency is the predictions are perfect. You want your algorithm to work well everywhere in between. And so smoothness to the quality of predictions is important as well. And so that's something people look at, limiting memory dependence. Another thing is that the hints that you're getting, the untrusted advice, may be coming from large complex models. It may be quite expensive to get them. Can you be frugal in your use of hints? Can you use them only a few times and still get these benefits from them? And vice versa, your online algorithm may require solving some massive non-convex problem. You might not be able to do that every time step. And you might have a very simple learning model that you can deploy. Can you still get robustness if you only need if you can only use your trusted algorithm a limited number of times? These are all interesting variations. When we come to, I think maybe the most interesting ones are, what are you predicting? So in this whole talk, I've been assuming that what's being spit out of the ML and the online algorithm is the action that it suggests you take. That's not necessarily the case. It could be trying to estimate your cost function. It could be predicting the availability of solar. It could be predicting parameters of your problem. How do you use those? What are the right inputs that are useful in the meta algorithm? There's a difference, right? If you give me an action, I can use it in one way. If you predict the next 20 cost functions, maybe that's more useful in terms of merging with the online algorithm than just getting the action, because I can compute your action from that anyway. And so what sort of information? And I think most intriguingly there, this is something that we're starting to work actively on now, is what if you take a gray box view of the AI algorithms? So suppose you're doing RL, suppose you're doing Q learning, and you spit out the Q function to the meta algorithm. This is lower dimensional than most of the actions, easier to estimate potentially, more data efficient, and gives you a lot more information about what's leading to that decision than just giving the decision. So the meta algorithm having that Q function maybe gives a lot more power in terms of getting around some of these fundamental limits that I talked about today. And so I think that's really intriguing. Then, I've ignored the learning aspect of this entirely, but how you do learning scalably in these contexts is really interesting. And of course, shouldn't be ignored. And I think maybe, the last one that, again, I think is really powerful is the design of these online algorithms. Right now, I've imagined treating them as off the shelf from, history of work in that world. But you can use training data to select those algorithms as well. So suppose, if we think about scheduling, the scheduling policy depends on, what sort of workload properties you have, whether things are heavy-tailed, light-tailed, what the distributions are between classes. You get a different guarantee depending on how you choose that. And so maybe you give up a little bit in your robust guarantee to tune which policy from a class of policies you're using for your online algorithm, and you still maintain a bound, but this becomes data-driven already in terms of the trusted advice you're spitting to the meta algorithm. And that, I think, can give a lot of power as well, is sort of data-driven algorithms inside of learning augmented algorithms. So you can sort of meta in that way as well. Okay, so with that, I will skip over my last section entirely because I've already gone long, and I'll stop there. So thank you.